Hi guys, in this video we'll be talking about equations reducible to exact differential equations. So we can sometimes come across a differential equation which is not an exact differential equation, or we can say is inexact. And to be honest, this is not uncommon, but it's not something to be worried about. When we encounter this kind of equations, there are a number of ways we can go about solving these equations. The first thing to do is to see if some other method of solving it exists. Say, for example, the equation is not an exact differential equation. If you realize that you can solve it using the methods for solving homogeneous differential equation or a Bernoulli equation, then we can go ahead to solve it using those methods. But there's also a third option, or there's also an option amongst the other options that we have. There's a possibility of converting this inexact differential equation to an exact differential equation. But how do we do that? We multiply this inexact differential equation by a suitable function that is known as an integrating factor. So basically, in summary, what I'm trying to say is you can convert an inexact differential equation into an exact differential equation by multiplying it by a suitable integrating factor. So this is one thing we need to remember because this is going to be very key in our derivations under equations reducible to exact differential equation. So by multiplying the inexact differential equation by an integrating factor, you're going to have an exact differential equation. So the next question we need to ask ourselves is, do we just multiply it by any function? The answer to that is no. And that's why I said a suitable function. There are rules governing the choice of the function with which we are going to multiply the inexact differential equation to arrive at an exact differential equation. So let's take a case study to look at what we are talking about. So that will further enable us to understand the concept. So consider this case study. We are given a differential equation minus y dx plus x dy to be equal to 0. Let's check for the exactness of this differential equation. So if you compare the equation that we have been given with m dx plus n dy is equal to 0, we notice that our m in this case is minus y and n is equal to x. So we can evaluate the partial derivative of m with respect to y. By doing that, we have our result as minus 1. And on evaluating the partial derivative of n with respect to x, we have our result as 1. So this shows that our dm dy is not equal to our dn dx. So this confirms that the differential equation, let me write that as dE, is not an exact differential equation. Or we could just say the differential equation is not exact. So now that we've confirmed that this differential equation is not exact, the next thing to think about is how do we convert it to an exact differential equation? And it's important to note that I'm not saying this is the only method to go about solving this particular differential equation. There are other methods. You could try using homogeneous differential equations. You could use separation of variables, amongst others. You guys can think about that in your free time. But for the purpose of this video, we are going to be focusing on converting this inexact differential equation to an exact differential equation. So the next question we ask ourselves is, To transform this differential equation, what function do we, this inexact differential equation, sorry, what function do we need to multiply it by to make it an exact differential equation? So let's multiply the differential equation under consideration by 1 all over y squared. So this means our integrating factor is 1 over y squared. Now let's multiply. Remember our inexact differential equation is minus y dx plus x dy is equal to 0. This is our inexact differential equation. So we can now multiply 1 over y squared multiplied by our inexact differential equation, which is minus y dx plus x dy will be equal to 0, because when we multiply 0 by 1 over y squared, we are still going to have 0 as a result. So we don't bother rewriting that. So this could be written as minus y dx plus x dy divided by y squared to be equal to 0. Or we could simplify it term by term by writing this as minus y divided by y squared plus x, sorry, there's a missing dx here, plus x dy divided by y squared to be equal to 0. So this means minus 1 all over y dx plus x all over y squared dy will be equal to 0. We can now test for exactness, because if we compare this with m dx plus n dy is equal to 0, we can see that m is equal to minus 1 all over y and n is equal to x divided by y squared. And it's important to note that this is just an assumption for the purpose of explaining how the integration factor works to convert the inexact differential equation into an exact differential equation. And there's a lay down method to get what integration factor or integrating factor, sorry, we are going to be using to obtain the differential equation. We are going to see that in subsequent videos. So let's go ahead to test for the exactness of this differential equation. So since our m is equal to minus 1 over y, you can see that the partial derivative of m with respect to x, so with respect to y, will be equal to minus 1 divided by y squared, sorry, minus 1 divided by y squared, and this gives 1 over y squared. Our n is equal to x divided by y squared. So you can find the partial derivative of n with respect to x to be equal to 1 divided by y squared. Now you can see that the partial derivative of n with respect to x is equal to the partial derivative of m with respect to y, which is equal to 1 all over y squared. So this shows that the new equation we have is an exact differential equation. Remember that the original equation we're working with is minus y dx plus x dy. But on converting it, or on multiplication by 1 over y squared, we obtained a new differential equation. So that's what the integrating factor does. If you multiply an inexact differential equation by a suitable function known as the integrating factor, we are going to arrive at an exact differential equation. So since we've successfully transformed it using the integrating factor, we can then go ahead to solve this new differential equation. So to solve the differential equation, let me go through first principle. Remember in our first video on exact differential equation, or I think the second video on exact differential equation, we used two methods to solve it. The first one was using the outline steps 1 to 5, with step 5 being optional. And the second one is to show how those steps were gotten. So just to refresh our memories, I'll be going for that method in this video. So if you've forgotten that, do well to check the previous videos that are on the channel. So we know that our solution is of the form integral of m dx plus ky. And we have said this is because if our z dx, the partial derivative of z, which is our solution, is equal to m, you can simply say our dz now is equal to m dx. And since y is going to be kept constant, we can write this as dz is equal to m dx. So in integrating both sides, we have the integral of dz to be equal to the integral of m dx. If y is a constant, which means the constant is going to be a function in y. So this further shows that z is equal to the integral of m dx plus ky. Remember, this is just to refresh our memories. So let's evaluate that. Our z is equal to integral of m that we got now is minus 1 all over y. Remember, it's the new exact differential equation, the one that was gotten by the transformation of the inexact differential equation that we are going to be talking about here. Dx plus ky. So let's evaluate this. So z now becomes minus x divided by y plus ky. And this is equal to a constant. Let's call it c. So recall that our n is the same thing as dz dy. So we can easily evaluate the partial derivative of z with respect to y. So this becomes minus into brackets x divided by y squared plus dk dy. And this is going to be equal to 0. So we have our n is equal to x divided by y squared plus dk dy. Sorry, this shouldn't be equal to 0. Take this out. So we also know that n is equal to x divided by y squared. Therefore, we have that x divided by y squared is equal to x divided by y squared plus dk dy. So we can see that dk dy is equal to 0. And when you solve this, we have dk to be equal to 0, and I'm integrating both sides. When you integrate 0 regardless of whatever it is you integrate it with respect to, say the y, you're still going to arrive at 0. So our decay dy, our k now becomes 0 plus another constant, c star. So k is equal to c asterisk. You can now substitute this in this equation. So z will be equal to minus x all over y plus ky. And this must be equal to a constant. So you can say z is equal to minus x all over y plus c asterisk is equal to c. And since c asterisk and c are constants, we could just combine them together. That leaves us with z is equal to minus x all over y, which is equal to d. We could decide to multiply it by minus 1. So we have z is equal to x over y, which is equal to minus d. We can then represent our new constant x over y, which is equal to, let's say, capital letter C now. And we have our solution to the differential equation. So this is the solution of the original differential equation that we were given in the first place. So just to chip in a little trick, pardon me or permit me to say that. So recall that when I wrote the equation after multiplying by the integrating factor, we wrote it as minus y over minus y dx plus x dy divided by y squared should be equal to 0. Now we can rewrite this. This looks a lot like the quotient rule from our knowledge of differential calculus. So this is the quotient rule states that v du dx minus u dv dx divided by v squared. So this represents d dx of u all over v. So in the same vein, we can rewrite this as d of u over v to be equal to v du minus u dv divided by v squared. Now this looks so similar to the expression that we have here. So we can see that our v is equal to y or minus y as the case may be. And u is equal to x. So you can either write this or you can say your v is minus y and u is minus x. So it's still the same thing. So we can write this expression as the differential or the derivative of x over y to be equal to 0. So by doing this, we can integrate both sides. On integrating both sides, we have the integral of the derivative of x over y to be equal to the integral of 0, say, with respect to x over y too. It doesn't really matter. It doesn't change what the outcome is going to be. So this becomes x over y is equal to constant c. And this is the same solution that we obtained using the outline. So recall, if you find easier ways to go about solving the differential equations, don't hesitate to opt for those methods because it just makes the whole process easier for you and shows that you have a great understanding of the concepts. Yeah. So in the next videos, we'll be discussing how to go about getting the integrating factors. Thank you very much for watching this video.